Welcome back to the Frontiers in Science, a conference in honor of Professor Yang at 100. Professor Fan and Associate Professor Wilkowski shall now continue to chair the remaining of the morning conference session.
Guys, welcome back. For our next speaker, let me introduce Professor Christos Panagopoulos. Okay, always forget this. Professor Panagopoulos' key research area is quantum materials, high-precision measurement techniques that provide multiple length scale and time scale windows. He connects the quantum materials architecture and the new device functions. His honors include European Young Investigator Award, European Excellent Research Grants, National Research Foundation Fellowship and Investigatorship of Singapore, and election of the Research Fellow in Trinity College, Cambridge, as well as the University Research Fellow of the Royal Society. The title of his talk today is Superconductivity-Magnetism Duality in Chiral Quantum Materials. Let me invite Professor Christos Panagopoulos to give the talk online.
Hello, thank you, Honjin. Good morning, everyone. I'm sorry that I cannot make it on time to be there in person. Let me share my screen. So I hope everyone can hear me. So it's a pleasure to be giving a talk in honor of Professor Yang. I will discuss our recent work on systems where solitons can drive quantum logic processes. The topic touches upon implications of his contributions on superconductivity, non-abelian statistics, and skyrmions, but in the solid state. Let me consider the parallels in the most fundamental interactions in specific superconductors and magnets, as shown in this slide. Take, for example, critical fluctuations near a ferromagnetic quantum critical point. These may favor low temperature phase, that is the magnetic analog of a superconducting state. Here, magnetic fluctuations may bind superconducting Cooper pairs with an internal angular momentum. Now, importantly, attractive interactions between magnetic fluctuations may force the ferromagnetic phase transition to become first order and to promote other types of order. For example, when the spins shown on the top right-hand side develop a twisted pattern, there is a similarity between this spiral state in a magnet and the prediction for superconductivity in the so-called FFLO state on the left-hand side of the slide. Now here, the phase of the superconducting wave function develops a pattern with a characteristic wavelength signifying Cooper pairs with a center of mass momentum. Now this connection indicates a profound link, as shown in the middle of the slide. Superconductivity on the left is formed from electron-electron pairs around the Fermi surface. Magnetism on the right results from electron-hole pairs as the electron fluid reorganizes itself. And this tells an important message. There may be a general mapping between exotic superconductors and different types of magnetic order. Quantum critical fluctuations, for instance, may favor superconductors where the phase of the Cooper pairs varies around the Fermi surface, as shown on the bottom left-hand side. Now, these superconductors have associated magnetic counterparts. Here, on the right-hand side at the bottom, the magnetic density varies in momentum space around the Fermi surface. In the strong coupling limit, this may lead to a spin-nematic electron liquid. This is a state with broken rotational symmetry, but without a periodic texture. One could also explore the superconductor-magnet duality with vortices and ask what would be the magnetic counterpart of a superconducting vortex. The answer turns out to be magnetic skyrmions, shown on the right-hand side. But actually both superconducting vortices and magnetic skyrmions are in fact topological solitons. Superconducting vortices on one hand consist of tubes of magnetic field lines surrounded by nanometer-sized swirls of electric current. Magnetic skyrmions, on the other hand, are shown on the right side. In magnets, appear in magnets with chiral instability. And here, the spins like to twist relative to their neighbors and assemble in circular patterns. Their non-trivial topology protects them from unwinding. Now let me bring in the operational aspect of this presentation. One approach for fault-tolerant quantum computers is operations carried out on particles so-called n-ions. Now, if you swap, as shown on the left-hand side, the positions of n-ions, the final state of the system will depend on the sequence of the individual exchanges. This path difference is useful to encode information robust against localized perturbations, which is why non-abelian n-ions are an appealing choice for qubits. A system actually that could host non-abelian quasi-particles is a triplet, so-called p-wave superconductor. It is distinguished, as you see at the bottom of the slide, from a conventional S-wave superconductor in the way that the spins forming the superconducting pairs are aligned as they carry the current. It is expected, in fact, that the constituents of an ion, n-ion, known as Majorana zero modes, should appear in so-called triplet p-wave superconductors in the center of the superconducting vortices that can form in these materials. However, these superconductors are extremely difficult to realize. Now, in theory, a conventional S-wave superconductor can be converted to a p-wave topological superconductor from combining Zeeman splitting, spin-orbit coupling, and conventional S-wave pairing through a real space non-collinear magnetic order, which is in fact is gauge equivalent to Zeeman plus spin-orbit coupling. Now say that we already have a topological p-wave superconductor. We can understand its topological nature by considering the momentum dependence of the phase of its wave function. Now, in a conventional superconductor, shown in the red disk schematic, the phase of the wave function is momentum invariant. On the other hand, in a two-dimensional topological superconductor, the phase develops a chirality, shown by the multicolor disk in the slide. It winds by an integer number multiple of 2 pi as you sweep through momentum space. Now, because of this phase winding, this state spontaneously breaks time reversal symmetry and develops chiral edge currents. You will find these exotic Majorana zero modes wherever you have a boundary in your topological superconductor, not only around its edges, but also at point-like defects, such as the quantized superconducting vortices that I mentioned earlier. Now, the bulk of a topological superconductor is actually gapped by the pairing interaction which creates the Cooper pairs that carry the superconducting current. Now, the subgap excitations in a superconductor are actually particle-hole symmetric due to the gap centered on the Fermi energy. Now, this has an important consequence. Namely, a zero-energy gapless state in a topological superconductor is an equal superposition of electron and hole-like excitations, and therefore it behaves as its own antiparticle. We call this gapless state a Majorana zero mode, which I will label from now on using pink stars. Now, there are two properties of Majorana fermions which give them advantage for storing quantum information. Firstly, the operator for an individual Majorana does not obey the Pauli principle, so it is meaningless to talk about the occupancy or the state of an individual Majorana zero mode. This is because a single Majorana zero mode can be considered as half of an ordinary fermionic state. Now, since the number of fermionic particles in a material is an integer, this implies that Majorana zero modes always come in pairs. And here the information is stored using the occupancy number, Na, of the fermionic state Fa, which is equal to 0 or 1. Now, for a set of Majorana pairs, the total occupancy number indicates the electron number parity in a topological superconductor. Provided that there is no spatial overlap between the two zero modes in a pair, the 0 and 1 states are degenerate, since a zero mode is a zero energy excitation. So if you have a total number of 2n Majorana zero modes in an array, for instance, you therefore have access to a remarkable 2 to the power of n degenerate states. The second advantage of using Majorana for computation arises from the fact that any pair of zero modes comprising a fermion can be arbitrarily distant. And this means that the occupancy of the state is immune to local perturbation. Now, in a calculation, the occupancy of each pair of Majoranas develops over braiding and evaluated by fusing two Majorana so their state degeneracy is broken. Until this readout via fusion, all information is stored non-locally and protected from decoherence. Now, the practical challenge, however, is to build a topological superconductor in order to create these Majoranas. To build a topological superconductor, there are three ingredients that we need to incorporate. First, remove spin degeneracy using spin-orbit coupling to remove one of the two Fermi surfaces of your system. In the remaining Fermi surface, the spin rotates as we move through momentum space. Next, we need to create superconducting Huber pairs from electrons with opposite momenta. So we need a simple isotropic conventional superconductor. And finally, we need to break time reversal symmetry using either static magnetic order or an applied magnetic field. Interestingly, theory for several years now suggests that spin textures mediated by so-called Dzielozinski-Moriya interaction in a two-dimensional chiral magnet can induce a topological transition to the exotic p-wave pairing in a neighboring superconductor. In fact, band structure calculations indicate a gapless state at the edges of a sample corresponding to a chiral Majorana edge mode. It also predicts that formation of a localized Majorana mode can happen in a vortex core. Now, calculations, moreover, that show that provided the sum of the Skyrmion topological charge and the quantized flux vorticity is an even number, then a Skyrmion vortex pair develops a localized Majorana zero mode in its core. It also develops a delocalized Majorana edge state at the boundary. So a few years ago, we asked ourselves if it is at all possible to develop a magnet superconductor bilayer in which magnetic skyrmions and superconducting vortices are coupled into pairs. And recently we demonstrated that we could build materials in which individual skyrmions create their own paired vortices in a neighboring superconductor. Now, our bilayer concept, as you can see here, is to deposit a type 2 conventional superconductor on a chiral magnetic multilayer. And for this to work, we had to clarify the interactions first between the superconducting vortices and the skyrmions in the respective layers, namely exchange coupling, which is spin polarization generating a supercurrent, and the stray field coupling, where the interaction is determined by the vorticity relative to the skyrmion core polarity. Now, for exchange coupling, the skyrmion-induced current must spatially coincide with a superconducting vortex current to reduce the free energy of the superconductor. Whereas for stray field coupling, we need to make the skyrmion radius as large as possible. And therefore, the skyrmion radius must be between the superconducting coherence length, psi, and the magnetic penetration depth, lambda. So here is the design of our magnetic multilayer. It works because the key magnetic parameters are tunable via the iron and cobalt thickness. Also because these parameters and the multilayer stray field can be modulated by the stack repetition of this multilayer structure. After a lot of experimentation, we selected several multilayers for a good balance between skyrmion stability, skyrmion existence range, and skyrmion stray field amplitude. And through a set of measurements with various complementary experimental techniques, we identified a multilayer that gives us a skyrmion radius of 47 nanometers. Now, over the past several years, we performed detailed investigations of the topological signatures and dynamics of these magnetic skyrmions, and confirmed their nail-type texture and the anti-clockwise rotation. Now, for the superconducting component of the bilayer, we fabricated niobium films with a thickness of 25 nanometers, and we find the coherence length to be approximately 10 nanometers and the penetration depth 200 nanometers. And these numbers satisfy the criterion for the skyrmion vortex interaction. The slide now depicts the essence of the material architecture we developed, namely the supercurrent and the superfluid density. Skyrmions in the bottom slab of the bilayer can be seen to nucleate antivortices in the top slab. These blue antivortices coexist with red vortices which are parallel to the applied magnetic field. The next task is to verify the occurrence of a topological phase transition in the superconductor, and this is ongoing work. Meanwhile, however, we are considering the technological potential of our quantum hybrid architecture. The Skyrmion vortex pair, and therefore a Majorana zero mode, should be intrinsically mobile. This means that we can eventually perform a non-perturbative, non-contact braiding operation without the risk of changing the electron number parity in our system. In other words, coupling the strong stray field of the Skyrmion to a magnetic microscope tip, we can move the Skyrmion vortex pair around the surface. So, as you can see on the slide, if we have two Majoranas to fuse for a state readout, reducing an external magnetic field will merge two nearby Skyrmions into a single stripe. And this creates an overlap between the two Majorana zero modes, which they contain. The occupancy of the Majorana fermionic state can now be proportional to the overlap energy and can therefore be read out in a computational operation. Now, our recent success to engineer nanodots, also shown on the left-hand side, allows us to also make an ambitious proposal for a completely new class of building blocks for quantum logic elements based on nanoskyrmions. These qubits are described by two parameters native to magnetic skyrmions: the topological charge, which is an integer that indicates how many times magnetic moments within a skyrmion warp a sphere, and the skyrmion helicity, which defines the spin-azimuthal angle with respect to the crystallographic axis of your material. Now, in skyrmions, which are only a few nanometers wide, helicity is a collective degree of freedom, and any value of phi naught corresponds to the same energy. Also, at sufficiently low temperatures, quantum fluctuations dominate, and a quantum mechanical treatment is necessary. And therefore, helicity and other classical quantities, such as the Z component of magnetization, are promoted to operators satisfying the usual commutation relations. So instead of classical energy, skyrmions can now be described by a quantum Hamiltonian in terms of these new collective coordinates shown at the bottom right-hand side of the slide. Now, to implement quantum algorithms using skyrmion qubits, you can manipulate the latter by gradients of microwave field with frequencies at the qubit transition frequency. And the transformed qubit Hamiltonian into the rotating frame reads as shown at the top right-hand side of the slide, where small omega is the external frequency, capital omega the external field amplitude multiplied by an envelope pulse function, and small phi the phase of the external drive. As an example, you can just see at the bottom of the slide of a qubit operation, for phi equals 0 and resonant driving, the unitary operator ux corresponds to rotations around the x-axis by an angle theta of time. In fact, we find that a skyrmion qubit operating from 2 to 25 gigahertz with a high harmonicity of 300 gigahertz has a coherence time in the microsecond regime. For this estimate, the operation temperature is at 100 millikelvin, and the transition to higher states happens at 2.5 Kelvin. The coherence time, in fact, that we find is already comparable to early measurements of the flux superconducting qubit and 2 orders of magnitude larger than the Cooper pair box. The number, in fact, of coherent Rabi oscillations within the coherence time is around 10 to the power of 5. Note that this number is inside the margins expected for superconducting qubits. Our next priority is to deliver experimental evidence now for the quantization of helicity and macroscopic quantum tunneling. This would be, in fact, a major result in solid-state physics, and it will also pave the way to develop 2-dimensional and 3-dimensional skyrmion qubit architectures and have control of qubit interactions. So before I end my talk, I want to thank my group for developing the hybrid architecture and demonstrating the skyrmion vortex coupling, but also our colleagues at Technion, Geneva, and Antwerp for the effective collaboration. And furthermore, I want to thank Dr. Christina Psaroudaki from Caltech and now in Cologne for making possible the work on qubits. More information on these topics can be found in these two recent publications. Thank you for the attention.
Thank you very much, Christos, for the very nice talk. So once again, you can scan the QR for raise questions to Slido, or you can just raise your hand. Professor Gong Jianbing, please, there's a question here. Can you send the mic? Yeah.
Yes, thank you very much for really inspiring talk. I just have one question. Could you elaborate a bit more on how are you going to use this architecture to scale up the number of qubits, Majorana qubits, so that you can really take best advantage of this quantum computing scheme to do actual quantum computing? Thank you.
Thank you. So I guess we are discussing this operation or the other one?
Either way is fine. Just I want to curious to know how. Yeah.
Right. In this case, in fact, we are able to now make in the pairs of these coupled solitons. So essentially, what you have is you have this skyrmion generating its own antivortex here. This antivortex would contain a single Majorana, and then the other one would contain its pair. So we can actually make many of these pairs, and we can actually move them around to braid. That's in principle the way that we can do this operation. So therefore, you can have multiple pairs, and in fact, we can do this now in zero magnetic field. You can confine them in nanodots and use that static energy in order to have magnetic skyrmions present in zero applied magnetic field. So therefore, you can decide how many skyrmions and therefore how many coupled antivortices in the superconductor you want to create. And therefore, you can have multiple of those, and you can start braiding in order to make computational operations. And you can fuse them, and by fusing, then you can have, that will be proportional to the occupation number. Now, for the other part, the second one, that is a totally different scheme. And here, you can actually make these individual skyrmions into stacks. Here I show you one example where we use the magnetic interaction between two different skyrmions in order to couple them with a little spacer, insulating spacer in between. But you can multiply this to make multiple of these independent skyrmions in a multiple array, in a big array with multiple skyrmions or skyrmion qubits. Mind you that the size of these qubits, in fact, can be just down to 2 or 3 nanometers wide, in the absence of an applied magnetic field as well, in principle.
Thank you very much. That's really exciting. Thank you.
Thank you. So, any other question, comments? Or may I invite some question from audience? Craig Liang Chan, are you around? Yes, no question. Gu Miller, you have any question? Okay, in that case, let me pick up one question from online, Christos. How would your research contribute to the ongoing development of quantum-based technologies, including quantum computers and quantum information systems? How far would this benefit tech companies such as Microsoft, IBM, and Huawei, and related business and budding entrepreneurs in the technology sectors?
So, as I described, or at least I tried to describe here today, for instance, in the second part, the skyrmion qubit, the information here is stored in the quantum degree of helicity, and the logical states are adjusted by external electrical or magnetic fields. Now, quantizing the helicity in a solid state is a major accomplishment, in fact, if it can be done experimentally. We have just shown this theoretically. So it's a completely new avenue. It's a completely new type of potential qubit where you use the quantum degree of helicity to perform computation. So in my view, this can actually contribute. It will not, we should view it as a complementary approach. Mind you that the results we get already are comparable, without optimization, are comparable to superconducting qubits, but also the Cooper pair box. So by improving the materials, which is fairly easy to do, at least by 1 or 2 orders of magnitude, we can actually become quite competitive in this direction.
Okay,
Right.
Thank you for the comments. Yeah, because of time, we also have to move on. Please join me to thank Professor Panagopoulos. Thank you, Christos. Okay, have a nice day.